guys will get to hook these very same circuits up yourselves and see if everything works the way I have claimed it does here in lecture. Any quick questions, administrative, logistical, things like that before we jump in? Okay, so just here's a reminder what we're up to. I have a 1 ohm and a 2 ohm resistor, and I have a 12 volt battery. Over here for reference is how they behave when the resistors are hooked up individually. And now I'm looking at the parallel configuration. So what makes it parallel is not necessarily that the resistors are physically parallel, but that they offer two different ways to get between the same two places, the same two voltage regions. So if you see here, I have my battery and I have my two resistors. They're not physically parallel, but if I separate this into equipotential regions, I only have two, A and B, higher voltage and lower voltage, and there's two different ways to get between them. So here's my little voltage waterfall, which indicates that between A and B there are two options, but both of those offer a voltage drop of exactly 12 volts. And so over here, as far as my voltages go, there's only one voltage in the circuit. The battery voltage of 12 volts, you can drop down the whole 12 volts by going through either resistor. So in parallel, voltage is the same, okay? So here's a summary of all that stuff. We basically have just this one box to fill in here. But the current is not going to be the same. If you present multiple options to get between the same two places, the same voltage drop, the current will not be the same. We work it out here using Ohm's law, and we find that 12 amps goes through resistor 1, while 6 amps goes through the other one. And hopefully that makes sense, because if you're given two options, but to get between the same two places, more is going to go through the easy way. So we have that 12 amps go through the easy way, but 6 amps decides to go the hard way. So that's about where I left off last time, super awkward spot. But let's talk about why this makes sense. So instead of having the routes between two different equipotentials, let's say there's two different routes between here and, say, CSM. Many of you take classes over there, right? Especially before we built the engineering program here, you guys would be going down there in a rush, okay? So most of you probably take the highway, right? That's the easy way, okay? But if the highway gets really crowded and there's absolutely no one on the local streets with all the stop signs and stop lights, a couple people might still take the back roads, right? So it still makes sense for a few people to take the hard way. So that's what we have going on here. We have an easy way, 1 ohm, and a hard way, 2 ohms. And while most of the current does go through the easy way, it still makes sense for some of it to go the other way. Someone's still going to say, hey, everybody's taking the highway, there's no one on the local streets, I'm going to take the local streets, okay? The only way that all of the current would go through one branch and none would go through the other way is if the easy way was truly free. In other words, it presented no resistance whatsoever. But as long as there's some resistance in the easy branch, there will be some current that goes the hard way, just not as much. And in our case, because this resistor is twice as much, it actually gets half the current. Okay? And as far as how to see that, since V is fixed for every branch because they're in parallel, Ohm's law dictates that I is proportional to 1 over R, which means if you double the resistance, you'll have the current. So here's what we have. We know that this river of current had a fork in it. We know 12 amps went one way, 6 amps went the other way. We can, of course, infer the total current. So if we had 12 amps that branched out one direction, 6 that went the other, that gives us a grand total of 18 amps. So 18 amps is the total current that's the current that flows out of the battery, then it reaches a fork, it splits off, 12 amps goes one, 6 amps goes the other, and then right here, of course, those forks come back together, so after that, it goes back to 18 amps returning to the battery. Now I want to point out that this is a lot of current, okay? You do not want to be touching something that has 18 amps going through it. And the reason why the current is so much, right? Certainly if you compare this to the series circuit that we looked at last time, the current was way lower than this. And that's because when you put resistors in series, it puts a big obstruction in your way. You have to go through all of them. But in this case, we actually can infer that because the current is so large, the resistance must be very small. And in fact, the current is not only much greater than the series circuit, it's actually much greater than either one of them even connected alone. So when we connect these guys alone, it's 12 amps and 6 amps, and when we connect them together like this, it's 18. So what we can conclude here is that if we are thinking of this as a circuit as a whole, which we often want to do, we want to think about what's the equivalent resistance of the entire circuit. Remember that the total current will flow according to how much resistance is in the way overall. You can apply Ohm's law not only to each individual element, but you can also apply it to the circuit as a whole. And what we are forced to conclude is that because we have so much current, we must not have very much resistance. So if this is large, this is very small. Okay? So the equivalent resistance of this entire circuit is very low. That's why there can be such a huge rush of current. Now we already even developed the law for how to do this last time, how to figure out what's the equivalent resistance of the entire circuit. It's a 1/over rule. And one of the things that we discovered is that the equivalent resistance is actually smaller than any of the individual members. So we found, it's in your notes from last time, that the equivalent resistance of this entire circuit is 2/3 ohms. And if you wanted to try to use this, you could of course plug it in here and calculate the total current. If you have 12-volt drop available and there's only 2/3 ohms in the way, you get 18 amps, which is of course exactly what we found. So that's a quick way to find the total current if that perhaps is your only thing you're interested in. So that's why there's so much current flowing here, is because there's so little resistance in the way. Now, question?
Is it because it's in a parallel, like when we're talking about like the 18 amps at the end of it, right? Or like the current everywhere, right? Is it just because?
So this is the current before it splits off into the 12 and 6, and then it comes back together into the 18.
Into 18. Is it because like some of them, like I'm trying to find the reasoning why it's less than.
That's exactly what I was gonna actually talk about before you asked the question. So I'm glad you're with me. So here's the thing. Here's my best analogy for a parallel circuit. So you guys have all maybe crossed the Bay Bridge at some point. You guys, they have a bunch of toll booths.
Mm-hmm.
Yes?
Mm-hmm.
Okay. Now, if it's rush hour, you really want them to have all of the toll booths open, right? You know, if you see that a couple are closed for maintenance or whatever, you're like, oh man, I'm going to be here a while. So in parallel, the more resistors you have side by side, the easier it gets to pass through. The same reason why you want as many toll booths open as possible. Because it's always better to have more options to get those charges through, right? And perhaps, strangely, if I added a third branch between these two equipotentials, and that branch was, say, 1,000 ohms, you might think throwing in 1,000 ohms would be a bad thing. Well, that's going to cause the total resistance or equivalent resistance to drop even further. It's going to lower it from 2/3 ohms. Now, why is that you can add such a huge resistor and make the resistance go down? Well, it's still better to have that branch as an option than to not have it at all, right? Before you had that branch, nobody could go through that way. The resistance was infinity.
I see.
But now you're giving at least a few charges that option.
I see.
So if you have a bunch of toll booths open side by side and one is closed for repairs, if now that one opens and it's the slowest toll booth operator in the universe, that's still better to have it there than not, right? So what you have in parallel is that every single option that you open will actually make the resistance go down. Now, yes, very few charges will go through this way, because as we talked about, most of the current will go through the easy way, less will go through the hard way, but it's still better to have options than not, right? That's the whole big thing of a parallel configuration. So in series, if you keep on adding resistors in series, it makes the equivalent resistance go up. But in parallel, when you add resistors in parallel, it makes the resistance go down, because you have extra options. You don't have to go through all of them. In fact, any given electron will only go through one resistor. But they're still better to have multiple options to get the charges through. So every resistor you add will actually make the resistance go down. Okay? Does that make sense?
Yes, sir.
Okay. Did that answer your question?
Yeah.
Okay.
It's just like.
So as far as our goal here, I said our nominal goal, obviously our main goal is just to learn what's going on, but we want to talk about find the current, voltage, and power in each element, in each resistor. We've now got the current in each one, we've got the voltage across each one, and now we need to find the power. And this is again where I like to have 3 different forms of the power law sitting around and available. They're all equivalent. This one I said I like for concepts because I times V, I lets me think about how many charges are passing through per time, and V is how much energy each of them is losing. But then I suggested this one for series. And the reason is in series, everybody has the same current, so it's hard to mess up plugging in the wrong current because there's only one current. So P is proportional to R. And so that allowed us to figure out that in a series configuration, the largest resistors have the largest power dissipation. And in fact, I called these big resistors the bottlenecks. Okay, so in a series circuit where you have to go through everything, you're going to have to pay the most attention to the big resistors, and that's where all the action is. The big resistors, they have the largest voltage drop, they dissipate the most power, okay? So I'm trying to develop these mnemonics. I'm developing them always in terms of the large resistor. The large resistor in a series has the most going on. They're the bottlenecks. They have the largest voltage drop, they have the largest power dissipation. Now, if you're wondering what's the last form of the power law for, as you probably guessed, it's for when you have parallel. So I suggest that you use this as the parallel. Again, it's not that the other ones are wrong. If you plug in the appropriate things, you'll get the same answer. But it's just much harder to mess up and plug in the wrong thing. If we were plugging in current, then there's 3 currents here in this circuit. There's I total, I1, and I2, and it can be easy to plug in the wrong thing. So in this case, you can't plug in the wrong voltage. There's only one voltage. Every element has the same voltage drop, which is the same as that of the battery, 12 volts. Okay? So, because we're holding something down so it doesn't change, we can then see easily what the other parts are going to do with each other. And P here is going to actually be proportional to 1 over R. So that actually tells us that the big resistors dissipate the least power. So we notice that everything is flipped here, that the big resistors, when you're in parallel, get the least current and the least power dissipated. So notice the big resistors here. This is where the least stuff happens now. Not the most, but the least. So instead of calling them a bottleneck, I'm going to call them a sideshow.
A sideshow, yeah.
Okay, it's not the main show, it's the sideshow. The reason is that if you have options, most of the stuff is going to go through the easy way. So the smaller resistors will get the most current and will dissipate the most power. It's the large resistors where a few charges were like, I'm not going to go through the fast track lane. I forgot my fast track today. There'll be a few things that go through the slowest toll booth operator in the universe, okay? Still some, but it is now a sideshow, okay? Does that make sense? You guys know what fast track is?
Yes, sir.
Okay.
It's mandatory, yeah.
I just realized not everybody has to cross the bridge regularly. Okay, so the big resistors, it's where the least action is, the least current, the least power. So now we can calculate that. Let's go ahead and do that. P1 equals V1 squared over R1. P2 equals V2 squared over R2. So I guess go ahead and plug my stuff in. This is a 12 volt drop. It's a 1 ohm resistor. So it's 144 watts. And then my other one, 12 volts squared over 2 ohms, and that's 72 watts. So again, it's not that the other forms of the power law wouldn't work, but you'd have to make sure to plug in the appropriate current to that resistor. And that's easier to mess up. And as predicted, since this resistance is twice as much, it's going to have half the power. They're inversely proportional. It's well worth looking at the conceptual version, P equals IV, and figuring out the comparison. Since V is fixed, it's the same energy loss per charge. That's what voltage is, right? It's the energy loss here per charge. So what is it that makes it so that there is much more power loss in the first resistor? Well, that's simply because more charges go through that way, right? So V is the same, but for resistor 1, so there is more current through resistor 1. So if you take a look at 2 electrons crossing the 2 resistors, they're both going to lose the same amount of energy. There are just many more of them doing that through resistor 1. So you dissipate more power through resistor 1. Okay? Are there any questions on that so far? Okay, so let's hook it up. The power is our window with the naked eye to figuring out if this stuff really behaves how it's supposed to. So let's make some predictions. I guess I'll write them over here. So what is our prediction as I hook this up? So first of all, looking at the 2 resistors, I do expect that the one that is a larger resistor will dissipate less, right? That's the sideshow. And the one that is the smaller resistor should dissipate more, okay? So the smaller R should be brighter. So that's one thing, is to compare the relative brightnesses to each other. And then the other thing we did was we thought about what is their power like compared to when they're connected alone. So let's compare. That's why I have these for reference here. And I've been carving out this little island and trying not to use this space. So, by the way, you guys are just going to miss it, but we asked that they put in a whole whiteboard across this whole wall, because between this board and that pillar, this is like the worst classroom to lecture in, because I'm trying to always find space. So anyway, here's the resistor one, 144 watts. What did it do connected alone? 144 watts. 72 watts for resistor 2. What did it do alone? 72 watts. So what we're expecting to see is that the resistor does exactly the same thing as if it was connected alone, even though it has a buddy. Okay? So we expect both to have the same brightness as they did when they were connected alone.
So long as you have enough amps to satisfy them.
Which is why I'm using a car charger. It's like using a shotgun to kill a mosquito.
Okay.
Yeah.
Are houses connected on series then?
So I'll get to that. So let's try it. So here's my R, and I'm going to connect that across the equipotential. So here's my higher voltage A, here's my lower voltage B, and here is my 2R. So here, notice that they happen to be physically parallel. That's not what makes them parallel. I can make them not parallel if you want. Okay, here, they're crooked, okay? So it has nothing to do with actually being physically parallel. It has to do with I have two options to get from higher voltage to lower voltage. Okay? So I'll go ahead and connect them. And I realize they're both blindingly bright. The one that's on the top also has frosted glass, so you're going to have to imagine that it would be even brighter otherwise. But I think you will see that the one on the top, which is the smaller resistor, is a little bit more blinding.
Yes,
Okay.
it is brighter.
So that is what most of the action is happening. This gets the most current and dissipates the most power. This is the sideshow, okay? So that hopefully bears out our first point here, that the smaller resistance is the brighter one. And to convince you that each of them has the same brightness as when connected alone, that's really easy to do, because I can just disconnect one and you can watch the other. So let me disconnect the bottom one, watch the top, see if it changes. Same thing, right? I'll do it the other way if you want to. I'll disconnect this, the other one couldn't care less, right? So indeed, they are exactly the same brightness as when connected alone. Now if you think about it, it makes sense, because you're connecting both resistors across the battery, the entire voltage drop, and so the voltage that drops across each one is the same whether or not there happens to be another one which is also connected across that battery. Both of them get the full voltage drop of 12 volts whether they're connected alone over here or they're connected with a buddy which happens to also be connected across that 12 volts. So if you have a given resistance, it's connected across a certain voltage, then the current and the power also have to be the same. Okay? So when you're talking about parallel, another way to think of it is completely independent paths. Okay? So each path is doing its own thing regardless of whether there are other paths or other branches. And how is it possible that if you have a bunch of branches that they can all get the exact same current as they did when connected alone? Well, of course, the total current that sources this whole thing increases just right. Because as you add more resistors in parallel, the equivalent resistance goes down and the total current being sourced goes up. Okay? So for instance, I can keep on connecting resistors here, and if I connect, say, another resistor in parallel, it does not make any difference to these guys. Okay, they're doing their own thing, like they're the only path in the entire circuit, and the other branches are irrelevant. So let me connect one more across the top here. Okay, and I can keep doing this. At this point, I'm not going to grab onto this anymore, because the total current that has to source all three of these branches is a lot. So the total current is going way up because now it has 3 mouths to feed. Okay? So all of these branches demand exactly the same current as if they're connected alone, but if you have 3 of those branches, the total current is very large. So the equivalent resistance was gone down. We've opened up 3 lanes on the toll plaza. The total resistance or equivalent resistance has gone way down. The total current has gone way up to source all of these branches. Does that make sense?
Yes, sir.
Yeah.
Okay. So that is the parallel circuit. Again, the big resistors are the bottlenecks in series. All the action, or most of the action, is there. And then in the parallel, the big resistors are the sideshows. The least action is there. Okay. All right. So now let's go ahead and do is start to see implementations of these in everyday life. So when would you want to use series? When would you want to use parallel? So let me draw a series circuit, like so. And let me draw a parallel circuit like so. Okay. So first of all, classic example of a parallel circuit would be the headlights on your car. So sometimes headlights burn out, right? But how many people here have ever seen a car that has only one headlight on?
Always.
Okay. So I know this is something where I grew up, you had a game where if you saw a car with one headlight on, you got to punch your passenger. Okay, I forget what it was called. It's like the punch buggy version, right?
Yeah.
Okay, so that obviously suggests that that is a parallel configuration, because if this light bulb burns out, then the other one stays on just as if the other branch, it doesn't care what the other branch is doing. This, by the way, a break in the wire is called an open circuit. So when they mean open, they don't mean like open for business. They mean open like opening or gap that you can't get through. Okay? So that is a feature, of course, for headlights, is that you want them to be independent. It would be really bad if one burned out when you're driving in the middle of the night and the other one also went out. That'd be a bad situation. That's exactly what would happen in series, right? If one of these went out, there's no viable path through anymore, the other one would also go out, right? And by the way, it does not matter if it's the first one or the second one. If there's no viable path through, the charges know right away and there's no current, okay? So here, if you had an open circuit, the current would turn off.
Shouldn't your whole car shut down too, since you have your spark plugs are all connected to the whole same electric system?
Your battery didn't break, it's that the filament inside your light bulb broke.
Oh, so each one of them has a circuit. Okay.
Yeah, so that's, a light bulb is just a resistor, and sometimes when it heats up too much or gets mechanically jostled, it can just break inside the bulb, right? It's like if a light bulb burns out in your house, it's not a problem with the electrical system of your house. Just put in a new light bulb, right? So, another example of parallel is Christmas lights. Okay, so Christmas lights, if one bulb burns out, you do not want the whole thing to go out. Okay, you don't want the whole. So, by the way that the Christmas lights are misleading. They look like they're in series. They're not. Okay, they used to be in series, and what you would have to do is once one bulb burnt out, the whole chain would go out, and you would painstakingly take out every bulb, try a replacement bulb, and if the whole thing lit up again, you guess you found the right bulb. And you just do that for however many hundreds you had. God forbid there were two bulbs that went out at the same time, then you'd be there forever. Okay? So the thing you have to be careful of is that Christmas lights are also in parallel, even though they look like they're in series. So what's going on inside a Christmas bulb, it may look like they're in series, but they are actually connected like this.
Yep.
So they look like they're in a row, but all of the bulbs have a link from beginning to end that is independent of the others. So they might look like they're in a row, but in that the cables leading between them are actually a bunch of smaller cables. Oh, excuse me. You have to not be so tied to the cosmetic look of it. To give you another example, a series could you could have it that the resistors are physically in parallel, but you just have to connect them like this. So that would be a series circuit that looks like it's in parallel. Okay? So the thing to really look at is the equipotentials. Are the resistors subdividing the voltage drops into a bunch of steps, or is every resistor offering a drop between the same two equipotentials? Okay? Now, question?
Would the Christmas lights that are in parallel require more power than the ones in series because they're?
So yeah, if each bulb glows the same brightness as if the other ones are not there, what that's going to mean is that the sum of them is going to dissipate more power, which is exactly what you want, right? You want each bulb to be as bright as it's connected alone, but now you have hundreds of them, so that you have hundreds of times the power dissipation of any single one. Yeah, and that's the idea, right? Christmas lights you want to be nice and bright, so a lot of power dissipated. So based on this discussion, I've obviously hopefully tried to convince you that headlights and Christmas lights, etc., you want to do in a parallel configuration, and you definitely don't want to do a series. But I do want to show you a situation where this right here, the fact that if one thing burns out, it shuts off the whole thing, where this is a feature and not a flaw. Okay? So that's something called a fuse. All right? So what is a fuse? A fuse is basically a little resistor. It's just a metal filament, and its whole job is to be cheap. So if you have a fuse that's in series with some extremely expensive piece of machinery that you have. So let's say you have that when you normally connect these two, there's a certain amount of total current that you're expecting. And of course, that is going to cause power dissipation in each one of these. The amount of power that's dissipated in each one, well, of course, the total current is the same through both. And then each of them you put in the resistor that's appropriate. And this expensive device that you have is expecting a certain amount of power dissipation. It may not be a light bulb, it may not glow, but as you know, electronics get hot. Okay, that's where the power dissipation comes in. And you need some way to get rid of that power dissipation so that the thing doesn't become too hot and overheat. Oftentimes you have like a fan, right? So your laptop might have a fan. That's what oftentimes is the noise that your computer makes. It's just the fan, that's all it is. So, what if the fan breaks? Okay, well, you don't want your computer to overheat and be permanently damaged, or whatever other expensive device you have. Computers don't usually have fuses, but you know, the analogy is the same. What happens if you have a current surge? There's an electrical problem, maybe there's a lightning storm, something happens, and the current surges. What that would tend to do is it would tend to increase the total current far beyond what you expect and dissipate more power, and now you're in danger of potentially damaging your expensive device. Well, luckily, the fuse is only rated to a certain total current, and if you exceed that, its whole job is to just burn out and become an open circuit. So when you go and you buy a fuse, you buy like a, whatever it is, a 5 amp fuse or a 6 amp fuse, whatever you're buying, that tells you that if the current through this fuse exceeds this value, it is designed to melt and stop current flow, not because you care about the fuse being damaged, they cost like 2 cents at the hardware store, but because whatever you're pairing it with, that would get damaged if the current got that high. Does that make sense?
Yeah, of course.
Okay. So, what you want to do very carefully is make sure that you're putting in the right fuse. Okay. If a particular expensive piece of machinery that you have requires, say, a 5 amp fuse, the worst thing you could do is accidentally put in a 10 amp fuse, because that means that you can get current up to 10 amps flowing through that, and well before the fuse blows out at 10 amps, you've already irreparably damaged the thing that is going through, because the device demands no more than 5 amps. Okay? So that's the idea. Anytime you go to the hardware store and you're buying these, you have to know what current you're going to go. The other thing that you need to know about fuses, just in case you ever need to get one, is not only do you have to get the right rating for the fuse, but there's also 2 types. They're called fast blow and slow blow. Okay? So fast blow is strict. If you exceed 5 amps, say, at any time, it will go immediately. Okay? And then you got to go back to the hardware store and get another fuse. If you get a slow blow, what that means is it's okay if it has 5 amps through it for a few seconds, as long as then the current goes back down below that. So it's not quite as paranoid about that, letting too much current in. The understanding that this device can withstand 5 amps for a few seconds, but if it doesn't go back below that very shortly, then the fuse should melt. Okay? So those are the 2 things about fuses that you need to shop for the right thing. And if you are not sure, if the casing of your device only tells you the amp rating, it doesn't tell you if it's fast blow or slow blow, obviously err on the side of caution, right? You want to get a fast blow fuse, okay? So those are more aggressive about shutting off the electricity when you have a current surge. This is much the same thing as a circuit breaker in your house. So you may have had this happen. You try to plug in 5 hair dryers, and then the electricity in the outlet goes out. That is a feature because you are threatening to, it's not so much you're worried about the hair dryers, but you're sourcing so much current to those hair dryers that you may have a risk of too much power dissipation in your household wiring. And you can start a fire behind the wall. So then the circuit breaker goes off. The only difference is that you go down and, well, you don't have basements in California, wherever it is that these things, the circuit breaker is.
Under the.
You go and you side of the house, you open up the panel, you see which one tripped, and you put it back. Make sure, of course, that you've unplugged your 5 hair dryers first, because it'll just trip again. But it's a mechanical reset switch. You don't have to go to the hardware store, okay? In fact, you may have here's some old timers, they don't call it a circuit breaker, they call it a fuse box. And that's because it literally used to be a bunch of fuses. So if your electricity went out, you'd have to schlep to the hardware store if you didn't plan ahead and get another fuse to go in there, okay? You had a question?
Plus the circuit breaker, we used to have like some ceramic type of fuses that like protected. Why would that happen? Like,
So there's many different designs for fuses, but this is just the general principle of a fuse. But fuse is generally referred to as anything that's a one-time use. If it burns out, it can't be reused. Whereas there's a different mechanism you can use in a circuit breaker that will allow you to just flip the switch back and restore the connection. Was there another question somewhere over here? Okay, so there's some just ideas of when series would be good and when parallel would be good. They both have their advantages and disadvantages. It really just depends on the application, okay? So sometimes parallel is good and series is bad, sometimes vice versa. It just depends on what you're trying to do, okay? So from here, what I'd like to do is to start building some circuits. First, I'll start with relatively straightforward circuits. We can take a look at the various features, and then we'll build up to more complicated combination circuits with many simultaneous parallel and series elements, and we'll solve and we'll show you how to get all the currents and voltages and powers in there. So my first circuit is going to look like this. Call this R1, R2. And I'm going to put in a switch on the side. So if that switch is closed, then there will be a wire in its place. And so this is not going to be a calculation question. I'm just going to simply talk about what happens to all the parameters that I might want to ask about when the switch is closed. So things that I might want to talk about. I1, B1, P1. That's the quantities associated with resistor 1. I2, P2, I2, B2, P2. Let's talk about what might happen to those. And finally, I might want to talk about I total and R equivalent. So things that are true for the overall circuit. So before I even close the switch, I might want to make sure I know what's going on before the switch is allowing anything. So this is before that, it'll be your standard series circuit. You have your highest voltage equipotential region. That is here. Remember, that's any contiguous piece of wire is taken to be an equipotential. Here is my middle step, B. Remember to circle any contiguous piece of conductor that's not part of the resistor. And then finally, here is my lowest voltage equipotential. So this is indeed a series circuit. There's a high and a low and a middle step, and I can draw in my voltage waterfall over here. So this is my initial, something like this, A, B, C. So whatever the total current is will course through R1 and R2. There's no other ways to go. And the voltage drops definitely won't be equal, generally speaking. Even though it's the same current, the voltage drop is not the same. The larger resistor, whichever one it is, will get the most voltage drop. So that's my starting point. So let's see what we can say about the switch closing in the 3 minutes we have remaining. So now we're going to close the switch. So now what we've done is we have extended C. There is no B anymore. There are only two voltage regions in the circuit, a high and a low. There's no middle step.
That's parallel, right?
In fact, in this situation, what is the voltage drop across R2 now? How much voltage drop do you get across here?
0.
None. That's right. So V2 has decreased to 0.
But it is parallel.
So Ohm's law tells us that if you don't have any motivation to go across R2 because there's no reward for you, then nobody's going to go through there. So V equals IR. If V is decreasing to 0, so does I. And so does P. So essentially, we have taken R2 completely out of the electrical flow. Nothing is going to happen through that. Another way you can think of it is that these two branches are in parallel, but one of the branches is totally free, so all of the current goes through here, whatever that is, and this current, there is none. This configuration, where you bypass the circuit component with a free ride, is called a short circuit. And by short, we mean like a shortcut or a bypass around that. In everyday language, short circuit sounds like a bad thing. It's again one of these things where it's a bad thing if you don't intend it. It's a good thing if you want it to happen. Okay? So, what happens with the resistor 2 is essentially might as well not even be there. It's completely removed from the actual electrical flow. It's a dead branch. That does, however, have an impact on the other circuit. It's not that we just get to take it out. It will have an impact on what happens with the other resistor. So let's take a look at that next time.